Thank you very much. It's a pleasure to be here. You are blessed with wonderful weather in Brazil. And it feels almost like you're not working but having holidays. Thank you very much for the invitation, and special thanks to my colleague and my co-author and my friend, Vertman, who we are actually working on a third paper together. And actually, he is my hero because he's doing mathematics despite sunshine and blue sky constantly working against him. So doing mathematics in Germany is somewhat easier, and I will tell you what comes out of that. So the title might scare you a little bit if you're not familiar with these things. So I will rather spend most of the time explaining you the basic ideas, what the Ricci flow is, for example, so that you kind of get slowly into the topic itself, even if you don't have any background. Okay? So I will talk first about what curvature on Riemannian manifolds means. So I will introduce these concepts, and then later on, I will tell you what the Ricci flow is. So I will tell you the Ricci flow, I will define the Ricci flow, and will tell you some applications. And these applications will tell you why this Ricci flow is so exciting to study. And then third part of my talk will be to discuss properties of the Ricci flow. And only at the very last, I will talk about stability, or say Ricci flow on singular spaces. Okay? So we're going to start slowly, and then at the end of the talk, hopefully, we are all smarter. Okay, part one. Curvature on Riemannian manifolds. Let's take an example. Let's consider a surface. It's a two-dimensional surface with holes inside, like a donut. And what is the Riemannian about that surface? I'm not sure how many people are familiar with Riemannian manifolds. If maybe people who know what a Riemannian manifold is could raise their hands. Wonderful. Wonderful. So I don't really need to talk about Riemannian manifolds. I just need to tell you that, basically you have a way of measuring lengths, angles, distances, and areas, right? So we know all of this works. And I would like to define the curvature of that manifold, of that space at some given point P. And I will start with something simple. I will start with an example being this sphere. On a sphere, which is also a Riemannian manifold, I can also measure lengths between 2 points, angles between 2 points, area. I could take 3 points and take the shortest connection paths between each of these 3 points. This will define for me a triangle where I have the angles alpha, beta, and gamma. And in fact, there is a fact that the following is true. The area of this triangle equals alpha plus beta plus gamma minus p. And just to make sure, yes, times r squared, where r is the radius of the sphere. So I can rewrite this equation and get the following. I can write it as alpha plus beta plus gamma minus p divided by the area. It equals 1 divided by r squared. And if I now let r go to infinity, this goes to infinity, to 0. So it corresponds to what we know intuitively. If the radius of the sphere increases, locally the sphere gets to look more and more like R2. And on R2, the sum of the angles equals p, so you kind of should approach 0 at the end. So this is the correspondence. Okay, but this fact is actually true on spheres, and I learned this about this approach to defining the curvature of a manifold from a friend, Wilderich Tuschmann from Karlsruhe. So I decided to share it with you. So what do we do with this now? Having this, I can now make a definition. I take my sphere, I take a point, I take my manifold, my surface, my two-dimensional surface, and take a point, any point on that manifold. I take a triangle where the sides are still the shortest possible paths, right? And I again have the angles alpha, beta, and gamma, right? I don't have that fact here because I'm not on a sphere. But still, I can measure the length and I can measure the area of that triangle. And I define a quantity, Kp, as the limit when the triangle gets smaller and smaller to that point P. So I don't make it precise. I write it in parentheses. So what do I take the limit of? I take the limit of alpha plus beta plus gamma minus p divided by the area of the triangle. Right? And this is what is called the Gaussian curvature. Basically, it is equal to 1 divided by r squared, where r is the radius of a sphere, which approximates my m tangentially as much as possible at this given point P. Right? So this is the Gaussian curvature. But the problem is as follows. The physicists have told us that the world is 11-dimensional. So we must be able to define the curvature in 11 dimensions, or whatever dimensions we would like, because the dimensions of the physicists change all the time, right? So what do we do in higher dimensions? Okay. Let us consider a manifold. Again, I cannot paint anything more than two-dimensional, but let's pretend it's a manifold of dimension m. And I have a point P here, and I have a tangent space at that point P. A tangent space is a kind of vector space approximating the manifold linearly at the given point P. Now, there is an exponential map that basically identifies a neighborhood of P in the tangent space, TPM, with a neighborhood of P here, right? And what it does is it takes straight lines and maps it to geodesics, to the shortest possible paths on the manifold itself. Okay? And of course, these paths go tangentially at the corresponding direction. Now, if you have that, you know, okay, so exponential p takes, let's say, straight paths and maps it to geodesics, which are the shortest possible paths here. And therefore, if I take a two-dimensional subspace in the tangent plane, E2 two-dimensional subspaces, they are mapped to two-dimensional submanifolds. That's the important thing. So you take a subspace, it's generated by, it's a two-dimensional subspace, it's generated by a basis of two tangent vectors. Each tangent vector defines you in an infinitesimal direction, and this way you can certainly, at least visually, understand that you will get a two-dimensional submanifold. So what happens now? We can now write the definition of curvature in higher dimensions. Definition. It's called sectional curvature. And what it does is the following. At a given point P, it takes two-dimensional subspaces of the tangent plane and maps it to real numbers as follows. You take this plane and map it to the k of exponential p E2. So this is the submanifold. It's two-dimensional, and therefore I can take the Gaussian curvature of this two-dimensional manifold at the point P. Okay? Is that clear? Or maybe I lost somebody. I don't want to lose somebody so early on. You know, later on, you know, things get complicated, but at least at the beginning we should pretend. Okay, so feel free to ask questions. Feel free to interrupt. I don't know what how it works in Brazil, but I'm very interruptible. Okay? Good. So this is our sectional curvature, and usually we can write our two-dimensional subspace as a span of two tangent vectors, and then we write the sectional curvature of E2 basically by saying that the sectional curvature is kind of applied to two tangent vectors. Okay, this is just a notation. Now, I want to give you a visual understanding what it means if this number is positive, negative, or zero, just to complete the visualization of the problem. So if the sectional curvature is bigger than zero, this corresponds to geodesics looking in this way. Like on a sphere. You remember a sphere? I just erased it. Very unfortunate. Then the geodesics start to look a little bit going up, but then they come kind of back to themselves. So the geodesics are positively curved. Geodesics positively curved. And this is called elliptic geometry. Okay. Now, what happens if the sectional curvature is negative? Then the geodesics tend to look like this. If you start at a point and you look at the geodesics, they get faster away from each other. And so geodesics are negatively curved. So this is the hyperbolic geometry. And now the simple case, the sectional curvature being equal to 0, means that our geodesics are actually straight lines. Okay? And this is then the Euclidean geometry. Okay. So this is the basic idea what curvature is, but it's too sharp. We would like to study average values of the sectional curvature because they're much more easy to handle. And this is where the other curvatures like Ricci curvature and scalar curvature come in. So let me define that. Again, I don't know, maybe some of you are very much familiar with this, some other people are not familiar with this at all, so let's hope this will converge later on. So other curvatures, the Ricci curvature is defined as follows. Is defined by taking the sum of sectional curvature, Ej x j equals 1 to the dimension of the manifold, where Ej is an orthonormal basis of our tangent plane TPM. Okay, so this is the way how you take averages. You take in the one component your orthonormal basis, and the other component is an arbitrary tangent vector. In this way, you define what the Ricci curvature is. Okay? I'm cheating a little bit, because the Ricci curvature is a little bit more general. In the Ricci curvature, you can actually plug in different tangent vectors. But I don't want to define this. So I give you only part of the picture. That's fine for the talk, I hope. And then the scalar curvature is again taking the average of the Ricci curvature. Dimension of Ricci curvature P Ej Ej. Okay. And this finishes our first chapter, the introduction to curvature on Riemannian manifolds. And we will now be able to study what the Ricci flow actually means. Okay, because Ricci flow comes in the title of my talk. Naturally, we should be able to define it. So the second part is Ricci flow and applications. Now, again, what is the Ricci curvature? Ricci curvature is a tensor which eats two tangent vectors, and it gives me a real number. Everybody knows what a Riemannian metric is, right? I wasn't sure. So it's again eating two tangent vectors and giving me a number. Right? It's a scalar product on the tangent space, which is then the reason why we are able to measure angles, lengths, study geodesics, and so on. So we see they act in the same way. So you could, therefore, discuss an equation relating both of them, and this is what happens in the Ricci flow equation. Definition. Ricci flow of a Riemannian manifold Mg is a smooth family of Riemannian metrics such that the following equation is satisfied. dgt dt equals minus 2 Ricci curvature of the metric gt at time t, such that at time equals 0 we have the original metric. This is Ricci flow. And let us try to understand intuitively what it does. Assume we have a piece of the manifold where the Ricci curvature is negative, right? Then we will see that the right-hand side is positive, and therefore the metric kind of blows up. So the Ricci flow blows up negatively curved parts, and let us do the same experiment for the positive Ricci curvature. We will see that it blows the part of the manifold down, right? So Ricci flow blows the positively curved part of the manifold down. And therefore, if, for example, we start with something which looks like a sphere, positively curved, it will actually blow down the manifold to a point. So the Ricci flow is not volume preserving. That should be clear. However, there is a renormalized version of the Ricci flow, which I'm not going to write down, which still exists, which is then volume preserving. So, but you should know that this equation is not volume preserving. This is not volume preserving because it will take a sphere and make it smaller and make it smaller and make it smaller, but there exists a normalized version. A normalized version. Okay. And this flow is actually designed to do one thing, to make a metric nicer. And the best thing possible would be if that metric would be Einstein. So Ricci flow is designed to try the following thing, to try to make a metric nicer into something like G star, where a Ricci curvature of G star equals some constant times G star. So this is an Einstein metric. This is what we would like to have. And basically, mathematicians are looking everywhere for these Einstein metrics, like normal people were looking for the Pokemons on the street a couple of years ago. It's the same issue. So this is the motivation. But let me actually write down some theorems where Ricci flow has been used decisively and therefore is so important. Okay? So applications, so famous applications. So first of all, there is the uniformization theorem. And I'm going to actually write out only a consequence of this uniformization theorem. And the consequence actually tells me that, that every Riemannian surface admits some metric such that the scalar curvature of this metric is constant. And yes, okay. So this is the uniformization, the consequence of the actual a little bit more general uniformization theorem, which says that every simply connected Riemannian surface is conformally equivalent to one of three types: the Euclidean, hyperbolic, or elliptic. And this has been proved by Hamilton in somewhere in the 80s using, let me guess, Ricci flow. Okay, what else? Second, geometrization conjecture, or Thurston's geometrization conjecture. And again, I will only write out the consequence. And the consequence is the Poincaré conjecture. And the Poincaré conjecture tells me that M3 simply connected and compact is actually homeomorphic to the 3-sphere. Okay? And this has been proved by Hamilton in 1981 in case of Ricci curvature being positive, the initial Ricci curvature being positive, and the general case has been done by the famous guy, Perelman. When? 2003, using Ricci flow with surgeries. Right? Everybody knows what who Perelman was, or sorry, is, and you know, crazy, very smart mathematicians, not only responsible for that, he is also responsible for a lot of in Alexandrov geometry, and he still declined $2 million instead of giving them to me, which is unforgivable. I'm gonna talk with him. Third result, differentiable sphere theorem. Again, using Ricci flow. Differentiable sphere theorem. So we have a manifold which is complete, simply connected, and the sectional curvature, and we now know explicitly what it is actually pinched, which means it's pinched away from 0 and stays somewhere between 1 and 4. Okay. Then M is not just homeomorphic, is actually diffeomorphic to the sphere. And this has been proven by Brendle and Schön. Guys at Stanford, Brendlin, not at Stanford anymore, moved. But again, using Ricci flow. Okay, so we should now be very much motivated to study Ricci flow. Okay, what is this equation? What are the properties of this equation? What is this stability of the Ricci flow, which is the title of my talk? All of these things you're gonna find out today. So now the third part of the talk are the properties of the Ricci flow, including stability. Am I too fast, too slow? Okay. My German friends called me and said, and complained, oh, it's raining in Germany. And I said, oh, it's really hot in Germany. At least we are both wet, right? Okay. Ricci flow. What are the properties? First of all, Ricci flow exists at least for short time. So it need not exist for all time. It can happen. It need not to. And is unique. So you can not have two Ricci flows coming out of the same metric. It's not possible. Now, a second thing is now a little bit more explicit. I want to tell you how the Ricci flow changes under diffeomorphisms, under very particular diffeomorphisms. So for people who know the field, I'm going to allude to the Ricci-de Turck flow, sorry, to the de Turck trick. So what happens? We have some time-dependent vector field. And this time-dependent vector field defines a one-parameter family of diffeomorphisms. So I have diffeomorphisms phi t from the manifold to the manifold, which are defined by my omega by the following equation. Right? So it's a first order partial differential equation with an initial condition. It has a solution. So this is the way you define one parameter family of diffeomorphisms. And now, imagine you have a solution to the Ricci flow. And you now use these diffeomorphisms to pull back your metric. So you define a new family of metrics by taking the pullback of the original flow. And I wonder what equation the new pulled back family of metrics satisfies. I can write it down explicitly. It looks very similar. It looks like this. But there is an additional term, the Lie derivative of G tilde. Okay? Now you may ask yourself, what's the point, right? Why making a simple equation more complicated? It's actually the other way around. So first of all, G tilde T is called Ricci de Turk flow. Where the choice of my vector field is a very particular choice. I don't make it explicit, but you can write it explicitly in terms of the metric. It's the de Turk vector field. So taking this de Turk vector field, you will get a new equation which is called the Ricci de Turk flow. And the reason for the Ricci de Turk flow is the following. The linearization of the Ricci de Turk flow is as follows. If I define an omega t by looking at how much my G tilde t differs from the original metric at the time 0, then this difference satisfies the following equation. Plus some quadratic terms in omega t. And this equation, where this is the Lichnerowitz Laplacian on two tensors, looks very similar to the heat equation. Right? It's a nonlinear heat equation where here we have a nice elliptic operator, a very good operator, the Lichnerowitz Laplacian, which is basically the equivalent of the usual Laplacian, but now acting on metrics, on two tensors. The Ricci flow itself does not have that linearization. It is not, it cannot be written down in the same way. Okay? So the operator there will not be elliptic if you write it out. So this equation is kind of simpler to do analysis with. And now you can say, okay, geometry is very interesting, but maybe I am an analyst. Right? Then you can switch on here, and you will still find things to do. Sorry? Q2, yes. I told it, I didn't write it. It's quadratic combinations. Quadratic in omega. Okay? Good. Okay. And I want to give you, so I'm still in this section about properties of the Ricci flow. There will be a reason why I'm actually telling you something about this linearization, but I also want to tell you something about stability. There is a very important property of the Ricci flow, an important property of the Ricci flow, which is called stability. So let me give you an understanding what this actually means. Do I see it correctly that I have 17 minutes?
Yeah, that's correct.
Okay. So, stability of the Ricci flow. I just write you a theorem with all the details. First of all, assume we have linear stability. Linear stability means that your Lichnerowitz Laplacian is actually positive, as you would expect from a Laplace operator. Second, you need to assume integrability. What is integrability? It means there exists a smooth finite dimensional manifold, manifold F of Ricci flat matrix. Ricci flat means the curvature, the Ricci curvature is 0. Such that the tangent space of that smooth manifold equals the kernel of the Lichner-Rovitz Laplacian. Okay, so there are two conditions. What can we get if we assume these two conditions? Then maybe I just paint a picture. The following is true. Imagine we have here our manifold of Ricci flat matrix. And I take a Ricci flat matrix here. And I take an epsilon ball around here in whatever topology. So I can take a metric here. It's very close to a Ricci flat metric, but it need not to be Ricci flat anymore. And I can now study the Ricci flow from that metric here, say G0. And the thing is, this Ricci flow will get down to the space of Ricci flat metrics. So you will get something here, which is then G star, G at time infinity, which is now Ricci flat. So you take your Ricci flat metric, you perturb it, let it flow with the Ricci flow, and it will get you back to the Ricci flat matrix. In this sense, the space of Ricci flat matrix is stable. You get out a little bit, you fall back. Right? So this is stability of the Ricci flow. Okay. So we have seen now, let's recap. We have studied the Gaussian curvature using triangles. Using triangles, we were able to define all the possible curvatures, the sectional curvature, the Ricci curvature, the scalar curvature. We have then defined what the Ricci flow is and discussed 3 theorems where Ricci flow has been used. And we have now seen a glimpse on the properties of the Ricci flow. One glimpse is that you can change the Ricci flow by a diffeomorphism and get something which looks like a heat equation. And another glimpse is that if you perturb a Ricci flat metric, you will get a Ricci flat metric back. Okay? So now our actual talk should be about stability of Ricci flow on singular manifolds. It should be about this result in a singular setting. So I want to present to you what singular manifolds are and why they're so important. Okay? Maybe I just erase this. So it's Ricci flow on singular manifolds. So I want to give you a model case, which is the basis of everything. The singular manifold, the simplest singular manifold, looks like this. So it's a Riemannian manifold with 2 parts, a compact part K and a singular part U. Now, K, G is compact with boundary being given by a smooth manifold N. And U is basically an open cylinder, open at the singularity. Here we have the radial function between 0 and 1, cross N. So it's basically a cylinder, right? It's topologically a cylinder. the singularity is in the metric. Why is it a singularity? Because I want G restricted to U to look of that form, to be of that form. We see this is the metric on the cross-section N. And as your radial variable x goes to 0, this thing gets smaller. So your cross-section gets squeezed down to a point. Right? So this is exactly, this metric gives you exactly that picture. Okay. And now you may ask yourself, why are singular manifolds important? So I will give you examples where, whether you like it or not, they appear. So singular spaces appear in quotient spaces. Orbifolds. They appear in algebraic varieties. They appear in moduli spaces. And I will give you examples for each, so that you actually believe me that you all should do singular manifolds, right? So let's say quotient spaces. I want to study R2 mod Z2, where I have the equivalency relation between x and minus x. So, of course, I want to identify this vector and this vector, with this being the fundamental domain. What happens? I take my fundamental domain, and I want to identify this part and this part together. How do I do this? I do this, chuck. What do you see? You see a cone, right? So you see a cone where here you have your equivalence class X. Okay, very simple example. Second example, algebraic varieties. They are actually submanifolds of CPN, and there are zero sets of certain homogeneous polynomials. So what I will write down will not be an algebraic variety, but it will be a zero set of a homogeneous polynomial. Very simple. I want to study x, y, z in R3, satisfying the equation x squared plus y squared minus z squared equals 0. This is a homogeneous polynomial, and you can all guess. Yes, exactly. This is x, this is y, and this is z. The zero set looks like two cones. Okay? Check it if you don't believe me. And I will not give you an example of moduli spaces because actually I don't have so much time. Okay? But at least it should persuade you that the world is singular. Okay? And therefore, if you don't do singular manifolds, it's your own fault. No, I'm joking, of course. Okay, so what are the problems in the singular world? We all know our world is full of problems. I'll list some of them. So so problems on singular manifolds, or in our world. One of them is poverty, and very close after that comes the fact that the Ricci flow need not exist. We don't know if it exists, and if we want to know, we have to prove. Second even if it exists, it need not be unique. You can have one metric where you flow out of the metric with two different Ricci flows. And I want to give you an account of the examples of the results in this direction.
It's not global.
Sorry?
It's not global. What do you mean by did not exist?
Okay, you can prove that it will exist under certain conditions. Under other conditions, it will not exist at all. Now I understand. Yes, it's not global. Right. I didn't understand the question. It's not global. Right, you can take xi and do a little bit of local constructions. Good. So one result, Giesen topping. It's 2011. What does he do? Do these two guys do? They take a singular surface, and this surface becomes instantaneously complete. The singularity is pushed to infinity. It's a flow. This is their Ricci flow. Miles Simon, 2013, takes something singular. Actually, the cone angle is kind of big such that it's actually only a Lipschitz singularity. But if you have a Lipschitz singularity, the Ricci flow actually smooths the manifold out. So you can have the situation that the singularity is smoothed out under certain conditions. Now, here I come, Vertman, and also Bahu Vertman, Vertman 2014, 2017, and also on surfaces Yin 2010. What do? We take a manifold which is singular under the assumption that despite the singularity, the Ricci curvature is bounded. You can have these situations. It's an assumption, it's a topological, geometric assumption on the cross-section. But it can be satisfied. If you have this situation, you can actually flow for short time and keep the singularity. This is what I was interested in. To keep the singularity and actually also to keep the cone angle fixed. You can flow under certain conditions. And also in Kähler, there is a Kähler Ricci flow which actually is in the center of the recent resolution of the Calabi-Yau conjecture on Fano manifolds by Donaldson, Tian, and various other people. In the singular setting, this has been done by Jeffers, Mazzeo, Rubinstein, Liu, Zhang, Wang, Cheng. Okay? So, but if you are in this business, these names are actually very familiar. Okay. So, I have like 2 minutes, and I will use these 2 minutes to tell you how you can prove that the Ricci flow exists globally. Okay? And this proof is actually, the way I present it, it applies to smooth manifolds as well, but the devil is, as usual, in the details. Okay? But I will give you an idea how to prove existence of Ricci flow. Okay? That's a good thing. The main result, I will not write down. It's stability on Ricci flow. This statement I wrote for the smooth case extended to the singular case. This is what I wanted to talk at the beginning, and then I came to Brazil, and the good weather made me nicer, and I didn't want to bother you with these details. So, proof idea for the short time existence. And maybe it's even interesting for other guys of you who are interested just in nonlinear parabolic equations. This is how it works. First of all, consider a linearization, or consider the linearization of Ricci de Turk flow. Remember, we just defined omega t to be g tilde t minus g0. And this omega t satisfied this nonlinear equation. It was on the board some time ago. What do we do with this? We see that actually, formally, it's equivalent to writing omega t equals the heat operator applied to the right-hand side. Right? And this is what I call f of omega t. And you can see basically what I want to do, right? I want to explain to you in the last 30 seconds that you can actually get your Ricci de Turk flow as a fixed point of a map F. That's all. So basically, you construct in the second step, construct scales of Sobolev spaces such that the following is true, omega s, such that Ricci curvature of G0 is in the, say, higher Sobolev space. You fix some regularity s. Your heat operator takes omega s and maps it to omega s plus 2. It increases the regularity. And if you apply it to something which is already of high regularity, it gives you even a time bound, omega s plus 2. And then you also have that your nonlinear term takes something in omega s2. It contains derivatives, and therefore it maps actually to omega s. And from there, you can actually conclude that that f is a map from omega s plus 2 to omega s plus 2, and on a subset which is defined appropriately, you can actually prove that it's a contraction. And that's subset. The contraction property requires us to take time small to make certain elements there small to make actually the contraction property work, and therefore you don't have an existence for all times, but only for short times. Okay? And the difficulty in the singular setting is, of course, to find the correct Sobolev spaces, to prove that your heat operator maps these Sobolev spaces as they are. There are intricate Schauder estimates. And then once you have done this analytic work, you get short-time existence of the Ricci flow. And then you can start doing geometry, like stability of the Ricci flow or existence of Einstein metrics and so on. But this is still work in progress with Klaus Krönke from Hamburg. (2018). Okay, thank you very much. Sorry for being over time.
The operator K2, I think if it's S is large enough, it maps into itself.
I can give you an idea how Q looks like. For example, Q omega t looks like the following. Kind of, and then you have terms which are like nabla omega t, nabla omega t, and so on.
So it's second order.
You will have derivatives of second order. And therefore, I don't see how it would actually preserve the order, because this order, by any construction you make, is actually somehow capturing the derivatives. And it has to be defined in order to capture the derivatives in Q2, exactly here.
Yes? In the case of singular manifolds, it looks like, okay, you really care about seeing when the Ricci flow is verified, unique, blah, blah, blah. Succeed application like uniformization type theorem.
Yes, exactly. I have one. So first of all, the joint work with Bayou from Seattle doesn't define Ricci flow, it defines Yamabe flow. And using Yamabe flow, which coincides with the Ricci flow in 2 dimensions, but basically is defined as follows: dt gt equals minus scalar curvature of gt times gt. So it is very similar to the Ricci flow. We could prove that if your original metric is of negative scalar curvature, your Yamabe flow, which actually exists for all times and converges to a metric which is singular and has constant negative scalar curvature. So you can use the flow to solve the uniformization theorem on singular manifolds. You can use maybe elliptic and variational arguments as well. This is done by Mazzeo and collaborators. But using the flow, this is what we have done. This is one application. A second application, okay, you can think of this as an application or not, stability of the Ricci flow. It goes further than just existence of the Ricci flow. I have proved that Ricci flow exists for short time, but actually the joint work with Klaus Krönke proves that if you start close enough to a Ricci flat metric, under certain conditions your Ricci flow exists for all times and converges to a Ricci flat metric again. So you can prove that even in the singular setting, the Ricci flat metrics are stable. What I hope will come later is an application where we can construct Einstein metrics on singular manifolds without the assumption of Kähler geometry. I mean, it need not be a Kähler manifold, and I still hope that under certain conditions, for example, positivity of the curvature tensor, we will be able to construct an Einstein metric. That's the idea. We are not there yet, but some applications are there already.
When you say singular manifolds, you are talking about manifold with just one singularity, or it can be more than one?
Exactly. So what we have studied are actually manifolds with edge singularities, where you have a fibration of cones which are not non-isolated anymore, but actually grow along some smooth base manifold B. So you kind of take your piece of paper and produce an edge. All right, this is an edge. There is a general class of stratified spaces. We didn't do stratified spaces. The reason why we didn't do stratified spaces is not the geometry, it's rather the analysis. Because after all, you need to study the heat operator in this stratified setting. And so far, there haven't been methods to discuss spectral geometry. It's a spectral analysis now in this setting. But recently there has appeared a preprint by Albon, Rochon, and Scher, I think, who have studied spectral geometry in this stratified setting. Actually, this is also the focal point of a joint project with Lewis. So we hope that we will be able eventually to do the analysis on stratified spaces and then extend the flow, existence, and all the other results to the stratified setting as well.
I have a question about that -2 factor. It's just a matter of convention.
I never thought about that. I would say yes, yes. Yes, you can rescale time and do whatever you like. Oh, the sign will be a problem, yes. Yes. Yeah, I can't pinpoint the reason why changing the sign is dangerous. But I haven't seen anybody doing this, and there must be a reason. I must admit, I'm an analyst. I came from spectral geometry. I was interested in the heat kernels. And only over time I realized that doing spectral geometry opens you a window into geometry. So maybe at that point I'm a little bit insecure why this particular sign. But only with this sign, you do have this thing, right? The thing is, if you change the sign, then you don't have a parabolic equation. But maybe, so from the analytic perspective, it's clear that it has to work with this particular sign only. The geometric perspective, I don't know.
So, let us thank the speaker again.